Hello, and today we're going to talk about Sun Part 3. I haven't done a Part 2 yet. That's basically dealing with solar anatomy, talking about the inside of the Sun, the outside of the Sun, sunspots, as well as talking about the chromosphere and introducing the corona. Sun Part 3 excuse me, is going to talk about the corona as well as something called a coronal mass ejection, and you can see the introduction to it down here. But again, never under any circumstances look at the Sun directly. Unless you've paid for a sunscreen of some sort, not even sunglasses. You don't want to get temporary blindness. You don't want to affect your vision at all. So please don't look at the Sun. Be wise. Wear protection. Be the cool one on the block. Okay, so what we're going to talk about today is we're going to talk about the corona. The corona, just like the beer in Mexico, stands for crown. You can see the corona when you actually block out the Sun. Sun is probably about this big, and this is actually from a site called Eclipse.com, and this is a total solar eclipse. This is the moon, moon being 400 times smaller, also 400 times closer, has the same apparent size as the Sun, which is 400 times bigger and 400 times farther away. So we have a very unique situation on this planet where we can get the moon. In both of these pictures, we can get the moon to actually cover the Sun, and if it covers it correctly, we get to see this beautiful corona. Just lines and lines and lines of it. If you actually draw the Sun, you probably draw it more like a corona, and now that you've seen this diagram, does it sort of look like a combination of those two? But that's a good way to actually draw the corona, but again, it's not visible unless you can block out the lighter part of the body of the Sun, the photosphere and everything down below. This is the corona, last layer of the atmosphere, the one that it extends out millions and millions and millions of miles away from the Sun. I'm not sure how the farthest extent goes, but you can see if the Sun is this big, these extend out much farther than just the actual diameter of the Sun. Okay, coronal mass ejection. The coronal mass ejection is any time coronal material is ejected. Very large amounts of coronal material is ejected out into space. Got a picture of one down here, and I'll actually show you an animation, or I'll show you a movie from YouTube in a few. But anytime we have a hole in the corona, and if you take a look, like this area right here, maybe some of this area, if you're looking lighter areas like right there, right in that area, this one actually is a pretty full looking corona. The corona acts like a barrier and actually holds material in. Coronal mass ejection sometimes can outdo the coronal ability to hold in these hydrogen ions. But basically they're hydrogen ions that are flipping out into space. They can't travel at the speed of light. Where Sun can make it to the Earth in about a little over 8 minutes, this stuff can take a day or a day and a half, sometimes even 2 days. Okay, so here is a hole in the corona shown by this orange line, and you can see they've got arrows drawn out here showing you this coronal mass ejection. It's throwing things out into this part of space. Now normally when we see these things, also like this picture right here, they're not really aimed at the Earth because we're on the Earth taking these pictures. So this one is going to go drop down over to the right, coming close but not there. This one in the picture, if this really was the Sun, we would be taking this picture, but they're showing you that the Earth is located right here. And notice they even have the 50% that's supposed to be dark and the 50% that's supposed to be light. Okay, so imagine the Sun throwing out lots of hydrogen ions. These things are streaming out into space. This is a picture sort of like what I had my kids in Earth Science do last period, and it also is in Sun 1, which is already up here on YouTube. But if you take a look at it, this is this flow of hydrogen ions called the coronal mass ejection. If you take a look at the Earth here, the Earth actually has this alignment. This is called the magnetosphere. Give you a really quick idea what the magnetosphere is. You guys have all seen magnets. Probably in school at some point you actually put a piece of plastic over the top, sort of like this, and you put iron filings on there, and you watch these iron filings. They actually come out of these magnetic waves come out of the south, but you watch these iron filings get these weird shapes on both sides of the magnet, and this is showing you the magnetic field. This is the magnetosphere. This is the magnetic field caused by the Earth's compass, north being up there and south being up there. Now the reason it has this funky looking look, some kids were telling me it looks like a jellyfish, is because this solar wind compresses the front side as well as pushes and elongates the back side. So it's sort of like I press these together and I pull these out in that direction, and it gets this view. I asked my kids to actually think of this as being like a force field. And when this solar wind material is coming out of the sun, and I didn't pick the color, when this solar material is coming out from the sun, it hits this force field, or the magnetosphere, and pushes some up and pushes some down. Now this will actually go until it can work its way through, and then some of it actually works its way back into this part of the magnetosphere, and actually comes in and will hit the upper atmosphere above the South Pole and above the North Pole. And what it does is it lights it up. It excites the electrons that are in the atmosphere and the ions that are in the atmosphere, and when these hydrogen pluses come down, they actually light up the upper layer up in the ionosphere. They light it up, creating all kinds of different colors, greens, blues, reds, all of which are called the aurora. We have the aurora borealis in the north. And we have the aurora australis down here in the south. So aurora meaning light. This is the light of the north, and this is the light of the south. Beautiful colors. Okay, this is what's called the coronal mass ejection. This is from SOHO, and what happens is they actually get, I can't really see where the pole is, but let's say the pole is right here. And this pole is attached to a disk, and behind the disk is the sun. So the sun is sitting right about there, and then we put a disk in front acting like the moon. We cover out more, and then this is a coronal mass ejection. Let me pick a different color. Lots of yellows, oranges, and reds on here already. This is the coronal mass ejection. And if you take a look, it's a massive expansion of hydrogen ions going out in this particular direction, perpendicular to the Earth, because again, we took this picture, we're back in the screen. This is going perpendicular, not going to affect the Earth. How much does this thing weigh? In terms of mass, hundreds of tons of mass of material. So the sun actually loses material. Not only is fusing it, but is losing it very, very, very fast. But it still has, we think the sun is 4.6 billion years old. We think it can actually live for about another 4.6 billion years. So if you do the math, we're going to make the sun about 10 billion years old when we finally finish this. But this is a coronal mass ejection going out in a perpendicular direction. If we were going to really watch this thing come toward the Earth, we would see this stuff coming out here, just getting bigger and bigger and bigger and bigger and bigger, as it came closer and closer, and within a day or day and a half, maybe 36 hours, 48 hours, it can strike the planet. And what does it do? It can cause aurora to actually move much farther south. I live in Virginia, outskirts of D.C., and I've been told that somewhere between 4 and 8 times a year we can see these, with the amount of artificial light that I do have. I've got a friend that lives out by Winchester. Gave me a call a week and a half ago when one of these large storms was headed our direction. Asked me to go outside to see these. I tried to go outside and I couldn't see it, and he was describing it to me and was actually seeing a pretty cool show. I was able to see these when we lived in Montana. If you ever get a chance to see it, you definitely want to try to take a peek. What else can it do to the Earth? It can blow transformers. It can actually light up electric lines. It can shoot down computer systems. You may actually find out that computers are going haywire. Supposedly, it can affect computer-guided airplanes, other things. We do some protecting of our electronics when this does happen, to try to get them out of harm's way. Okay, Eclipse II. I did a video on Eclipse earlier, but basically we have two different types of an eclipse. We have a solar eclipse and we have a lunar eclipse, and it kind of all depends on who gets blocked out. On this picture right here, we are actually seeing that the moon gets in the way of the sun, blocks out the sun. This is a solar eclipse, and it actually says so right there. Okay, what's the moon phase? Lit side of the moon's towards the sun, dark side of the moon's here. This has got to happen during a new moon. Okay, this is a Earth blocking out the moon. This is a lunar eclipse. What moon would this be? Well, if the Earth wasn't in the way, the visible side of the moon would be facing the Earth. And this is going to happen at full moon. And this is new moon, and we got the moon right there. When we do it, I had the kids do what's called a ray diagram, and we actually learned that between the top of the sun and the top of the moon and the bottom of the sun to the top of the moon and the top of the sun to the bottom of the moon and the bottom of the sun to the bottom of the moon, we actually do get a pattern of eclipse. If we actually looked at the Earth, what we would notice is we would see a really dark center section, like right there. This is caused by the umbra part of the shadow, and you can see here umbra also, the darkest part of the shadow, and it would be actually covered with a round, fuzzy, round because the moon is round, a round fuzzy area that would get more and more dark as we got closer and closer to it. Would look something sort of like that, darker in the center. This would be the penumbral part. If you live in the penumbral part, you're experiencing a partial eclipse. And if you live in the umbra, you're experiencing the total. Now, a solar eclipse umbra is very small, covers a very small part of the Earth. Maybe 3 or 4 or 5% of the planet get to see a total solar eclipse. If you take a look at this, during this lunar eclipse, everybody on this side, and because the Earth's shadow is larger, it can take a few hours for the moon to get through this, where we can actually rotate in and rotate out. We can get 50 to 60% of the planet seeing a lunar eclipse. They happen just about the same amount of time, but many more people get to see the lunar eclipse, and this is why you pretty much say, I've never seen a solar eclipse, or I don't get to see very many of them, because you have to live in a very specific point. We get an eclipse like every 9 to 14 months, but we actually have these things there. And then this thing is actually going, and we're still going. We got 13 minutes, so I got to get this thing moving. But if you take a look at it, we have, I've done everything. That's a full moon, penumbra, umbra, total eclipse, partial eclipse. This would be a total eclipse. These are partials. Sometimes the moon only moves through the penumbra, so all we get is a partial eclipse. Sometimes it actually gets part of it into the umbra. That's still called the partial eclipse. Okay, now why don't we get one of these every time we get a full moon or we get a new moon? Well, the moon's axis is actually tilted a little bit more than 5 degrees from the sun's direction. So the only two places you can get an eclipse is if the moon is right there and the moon is right there. This is called the descending node because the gray line is the moon's orbit and it's descending down to the sun, apparent sun's orbit, the ecliptic. And then this is called the ascending orbit because it actually, or the node, because it actually comes up as its orbit crosses the ecliptic once again. So if you get a full moon or new moon there, you're going to get an eclipse. If you get a full moon or new moon here, you're going to get eclipse. If it's a full moon right there, the Earth is blocking out the sun, that would be a lunar eclipse. If it's a new moon right there, sun's in the same sky and it just got blocked out again. That 400 times smaller and closer for the moon, 400 times larger and farther away for the sun. Okay, going down to tides. We basically have 3 different types of tides. We have things that are called spring tides. Spring tides happen when the moon is located right there. What phase is this? Visible side toward the sun. It either happens at a new moon, and the moon goes around in a counterclockwise direction. This is supposed to be an animation, but it's not. It can also happen at the moon at this location. And what moon would this one be? This one would be a full moon. Moons happen 40% by the moon, 60% by the moon, 40% by the sun. Then we actually get the moon to go all the way around again to this one again, and we get spring tides. Spring tides really do happen probably from this location to that location, and this location to that location. But the biggest one would actually happen at new and full moon, just like Neap tides. And what color am I? Moon's going around this way. It was new moon when it was right there. This would actually make this the first quarter, or what's called the waxing quarter. And then it's going to move over this direction, back over to this side, and this would be the third quarter, or the waning quarter. This is the waxing side, and I have a thing on moon phases also. This is the third quarter. So anytime we get a moon in the third quarter or the first quarter, again from probably like right there to right there, we get what's called a neap tide. And the reason this is called a spring tide is the 40% yellow, which is the solar tide, and the 60% moon are all pointed in the same direction. So we get this big blob of water. If you rotate, which the Earth is actually rotating in this direction, if you rotate into that blob, you're experiencing a high tide. You rotate out, you're getting a low tide. This is the highest high tide, as well as the lowest low tide possible. If we remember when we talked about earlier on another video, the Earth, moon goes around in an elliptical orbit. Sometimes it's actually closer, sometimes it's actually farther. If we do get this spring tide to happen at what's called perigee, we can get the biggest, highest high tide and the lowest tide imaginable. And if we get it over there, then the high tide's not quite as high and the low tide's not quite as low. Because we're pulling more water into the high tide, that means it's got less water for the low tide. Excuse me. If you look at the neap tide, there's the 60% from the moon, there's the 40% from the sun. So what happens is, as the Earth is rotating, this low tide isn't quite as low as the last one, and this high tide isn't quite as high. So we get what's called the lowest high and the highest low tide possible. These guys, remember, it's 29.5 days to go from new moon to new moon. So we get these about every 2 weeks. We get spring tide to a spring tide about 2 weeks later. About every week we go from the spring tide to the neap tide, a neap tide a week later to the spring tide, and then a week later to the neap tide, and a neap tide back to the spring tide. And then what's the moon between like that area and this area? These are what are called normal tides, where we get the normalist high and the normal low. One really good example of all this is what's called the Bay of Fundy. The Bay of Fundy is a location up, and you can see here's Maine. It's on the southmost eastern side of Canada. Nova Scotia's right there. But what happens is when the tide actually comes into this location, it gets concentrated. So what happens is we get a lot more normal tides go up a couple of feet. You can see this is 6 meters, 23 feet, 26 feet, 30 feet, 33 feet, 36 feet. Let me just make sure you guys can see all this. And then it goes up here, and when it gets even more narrow, it can go up to 46 feet and all the way up to 50 plus. I think the normal is 52 feet. Give you an example. Here are some boats tied off to a dock. This is what it looks at low tide. Now you have to make your boat hull fairly strong if you're going to bring your boat up there. You probably even have something to keep this thing from rolling over, but you know that the water's going to come right back in and float it back up. If you're going to be a fisher person, a fisherman, fisher lady, fisher person, you better pay attention to high tides and low tides, because if you want to go out there to get there at 6 in the morning out there, you may have to leave at 6 the night before to actually catch the water so you can go out there. And I've been in this location, probably up in here, and there actually is what's called a tidal surge, where just like a wave of water rushes upstream. It's very wickedly wild to watch water actually flowing downstream, but watch this wave come upstream. And we even rented inner tubes, and were able to float, except we showed up a little late, so we weren't able to do it, but we watched some other people do it. This is also in the location. These are sandstone cliffs that are being inundated by waves. Eventually this will get so thin this will topple over, and again that'll topple over. But for right now, these are like pillars that are standing up in on dry land. It's actually kind of muddy, but it still is dry. And then you can stand out there as the water comes in, and then you better clear. There are steps that take you back up to the shore because the water comes in, and then you can actually bring a kayak and go into that area. Okay, I think that'll about it. And again, we talked about tides. We went over the eclipses again, talking about the nodes, that's new. Coronal mass ejections and their effect on the planet. Solar wind and its effect on the planet for auroras. And then, please, never look directly at the sun. Thank you much. Bye.